Okay, so in the part 1 actually we have seen how to set up this turn in place state machine, including the states and the transition rules, plus how to set this turn in place anim sequence at the data table, right? And just for the demonstration, I think I have been hard coded this value at here. So if I play test it, now you can see that turn in place is applied, right? But now let's determine that value on runtime instead of hard coding it. Okay, so I'll change this back to 0, compile and save. If I play it again, now you can see no turn in place animation has been displayed. Okay, right, and then let's see how we can set this root offset value. Okay, so let's go to this blueprint thread safe function, and here let's let's create a new function called what, update root your offset, right? And let's move it as this, move it to this blueprint thread safe functions category. Okay, and then do we have a reference for the delta type? Yeah, we have a reference here. So let's go to the function again, and as the input I'll give a new parameter called delta time, which is float. Okay, and then there are a set of complex calculations that we have to perform. But first we have to determine our root years offset mode as well, because sometimes not actually sometimes, at each time whenever we rotating, we have to determine whether we are keeping the root year offset as it is, or whether we are blending it out, or whether it should be accumulated, right? Because with this delta time, this root year offset should decrease, and then it will come back to the idle state and play that idle animation instead of keep playing the turn in place animation. So in order to determine that states, I'll create a new enumeration called e root your offset mode type, right? And there are 3 types. First one is blend out, second one is hold, third one is accumulate, right? And let's save all and go back to the ABP locomotion, and I'll create a new variable called root your offset mode, and its type should be root your offset mode type. right? Okay, so first, if we are not moving, which means we are remaining at the idle state, then let's see how we can calculate the root offset. So if this one is accumulate, let me be assign the sequence. This one is accumulate. We have to get the existing root to offset. Do we have your delta since last update? We have the your delta since last update, and I think this one comes from world rotation, right? Here the set update rotation data, actually we calculate that your delta since last update, so we can use it here as well. Let's get the difference, and alongside we have to set the root to offset. Therefore I'll create a new function called, not a variable, a function called set root to offset, and assign it to the new category called turn in place. And this function should get the root to offset. So I'll mark it as maybe, I rename it as root to offset. And let's go back to the root to update root to offset function. And there let's call this one like this, right? So I'll implement this function later on, but first let's finish this update root to offset function. Right, so that's for the accumulation. I'll mark it as accumulate. Okay, and then the next type is blend out. And if you are blending out, then the root to offset should be calculated in a different way. Yep. So shall we get the float spring interp like this, compile, and we need the reference to the spring state, so I'll promote this to a variable called root to offset spring state. Yeah, now that error has been gone. And as the current state, let's use the existing root to offset, and as the delta time, we have this delta time, and all other configurations are fine. Yeah, except stiffness should be like 80, and the critical damping factor, let's mark it as 1. So this is stiffness determine how much rate this float interp should happen, right? The target is 0, which means this root to offset, let's say if it is 60, with the time it will become 0, right? This is an interpolation of between two values. Okay, and then we have to set the rotation root to offset as well as the return value. right? So this is the basic interpolation that we perform to make the root to offset back to 0 from its existing value. So I'll comment it as blend out. Okay, and I'll add another pin, and at the end of the accumulation and the blend out, the root to offset mode should remain at the blend out state. So therefore, I'll set it as blend out and assign it to here. Right. So that's the update root to offset function. And let's go to the blueprint thread safe update animation. And at here, let's plug that set root to offset update root to offset function. Right. And as the delta time, we can provide the existing delta time at this blueprint thread safe function. Compile. So make sure to mark this update root to offset function as thread safe, otherwise this will give an error. Right. Also, we have to make this set root to offset function as thread safe, and now the error has been gone. Okay, so now we have this update root to offset function, which is keep updating this root to value. Now we can implement this set root to offset function. Right. So I'll rename this one as maybe in root to offset. Otherwise, we will be having some issues with these variable names because we have the existing name root to offset as a global variable here as well. Therefore, I'll rename this one as in root to offset. And there, let's normalize the axis, right? And I'll get this root, sorry, not this one. Actually, we should have root to offset angle clamped value as well. But how to add that thing to here? Yeah, maybe we can add this as a configuration at the data table level as well. But for now, since I'm focusing on this implementation, I will create a variable called rotate root to offset angle clamp, and the variable type should be vector 2D. Right, but we have to assign this we have to take this value and assign it by using this data table and imset configurations, but let's add that record later on. But first, let's implement this function, and I can split it, or maybe I can break it, and let's clamp this angle based on minimum and maximum. Right, and if these are equal, we can make a select float. If these are equal, then we are getting the remaining normalized value. If these are not equal, we are getting the clamped angle based on this clamp value. Right, and then we can assign this root to offset at here. And maybe sometimes we may need to disable this root to offset as well for the performance reasons. Like let's say when we are at the different animation level, sometimes we may not need to play this root to offset mode animations. Therefore, we may need to toggle these values dynamically. So I'll add a new variable called disable root yo offset, which is a boolean value. So by toggling this boolean value, we may be able to disable the root offset. Therefore, I'll add a new select here. This one, select float. So if this one is true, we keep the root to offset as 0, and if this is not true, which means the root to offset is unable, so we are taking the processed value, and let's attach it to here. Right, so I'll move this one to turn in place top level like this, and now root to offset is done, so I can move it to the root to offset category, and root to offset mode is also done, and spring state is also done. And we have to resolve this variable now. Okay, so how to get this value? Yeah, let me quickly look at the documentation. Yep, so let's go to the data structure level. We have this SNM config. So here let's add a new field called rotation root to offset angle clamp, which is the type of vector 2D. Right, and as the default values, I'll assign -120 and 100. So those are the maximum rotation angles that we can achieve for a turn in place, and the actual turn in place root to offset value will be clamped in between these two values. Right, okay, now I'll save it all, and let's first check the SNM set data structure. Yeah, as usual it has been broken because S movement group is now changed. SNM movement type, SNM movement type, where is that one? Yeah, this one, it's good to go. This one is not good to go, that's the issue. So let's reassign it. Yeah, now it's good to go. Then the movement group will be assigned at the SNM set. So let's reassign it, and this one is also fails because This anim general. It's also failing because of this one is anim sprint. It is good to go. So I'll reassign it. Now that one is also good to go. And let's reassign this one. Still failing. Boolean. Yeah, now it's good to go. And finally, dt anim set, save. And as expected, everything will be lost now, but nothing to be worried because we kept a dump there. But ideally, let's go to this BPC component and compile it. Right, so it has been compiled properly. Okay, so let's go to the data table again and let's check our new movement configs, and it is there, but I think the values has been lost. Maybe we can check it again. Yeah, we have the config. Yeah, this one. Yeah, the values are there. So I'll copy the values back to this print config, paste it here. And any movement config, paste it here. Now let's see the table config values. Yeah, it's still not there, but that's fine. I think we can quickly assign it to here as well. But first let's re-import the JSON file. So here you can see we have one called re-import, right? So if you select it and select this dt anim set JSON dump, so it will say set of stuff has missing entries because this entry has been added by us recently. So these warnings will be there, that's fine. Simply click OK, but the remaining data will be assigned properly. Right, you can see all the cycle directions, pivots, all the crouch, stop stuff, everything is there. The missing part is basically this root to angle clamp value. So let's copy that value from here and I'll place it at each record. So work config and job config, and finally crouch config. Save and let's export it back. So we have the latest dump there. Okay, now that angle clamp should be taken from this data table to this ABP locomotion graph. But first I'll compile this one and compile this one, and here we have not thread save function set animation data. Where do we get this value? Yeah, maybe we need to create a new node, a collapse node graph to set these configurations. So I'll add a new pin here, and how to get the config. So at here we have the movement struct. So I'll move it aside, and let's get the movement struct, break it, and here we have config. Let's promote it to a local variable called lconfig. Right, and let's hide the unconnected pins. Compile, then we can get this config, break it, and we need this variable to be set like this because this variable was already defined at this ABP locomotion graph. So I just need to reassign it based on the data table value. Connect it to here, hide unconnected pins. Let's collect the node. Mark it as configs, and like this. Okay, and finally I can move this to turn in place as well. Okay, right, now I think we are almost done, but still I believe the root yaw offset should be further calculated, but let's play test it now. Yeah, as you can see, still the root yaw offset is not updating properly. If I try to debug this using event update, let's print it. You can see even if I try to move rotate, still the root yaw offset is not updating, right? So let's add those processing logics at the third part of the turn in place, otherwise this session will be also too much longer, right? So at the second part of the tutorial, what we have been done, how to capture this root yaw offset mode properly and assign it using this set root yaw offset function. And now we need to process these root yaw values and assign it, update this variable according. So we'll see how we can do those stuff in the third part. Thank you. See you there.